Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. Welcome everybody to this very first lecture of this introductory course on ergodic theory. So this is going to be a short course of 4 to 5 lectures, and where we will talk about and will introduce basic ideas, concepts, and will state important results, will prove important theorems. And the aim and goal of the course is to give you enough and necessary tools which make you able to study the course further by yourself. And of course, you can reach to us at any time through our emails. You can find all our details in the site of mathsvolunteer.com. And I will also attach the necessary links in the description, which will make it easier for you to reach to us. So without further delay, let's begin today's lecture. So today we are talking about what actually we study in dynamical system, and will give a bit of motivation that the things that we are studying is actually are important and will make our life easier. We will also give some definitions and will state some important theorems from functional analysis. And toward the very end of today's session, we will also prove a theorem which will be, of course, related to this course. I'm trying in today's lecture to make it appropriate according to the title, and will ensure that actually physical measure and theory importance is a right title for today's session. So let's begin with the motivation. Well, right from the beginning, the very first goal of dynamical system is to describe the typical behavior of the trajectories. And of course, as always in mathematics, we are interested when time goes to infinity. Well, describing the trajectory associated to some particular point under, let's say, under some map, it is not always much informative when you are dealing with it topologically. For example, topologically, you can't get much information about the frequency with which the orbit is visiting to some specific region of the space. And so, for this reason, we in this and many other this kind of reason, we introduced the ergodic theory, and in fact studying the orbits from another point of view, which is the statistical point of view. In order to make these points clear, like the goal and then the topological approach, let me give you some examples which will make it easy for you to understand that what I want to say actually. So let's go back a little bit and see what is orbit. So you have map from a space X to X. I'm not specifying. You can think of X as a topological space, as a metric space, as measure space. So for any point X naught, for any initial condition X naught, the orbit associated to that point X naught, in fact, I'm dealing with only the forward orbit, is actually the sequence or the set that we are getting from the forward image of that point. Well, in fact, what should we ask, and what are the questions that we are supposed to ask from ourselves about the orbit? Let's see. Let me give you a couple of questions that we need to ask about the orbit from ourselves. For example, we can ask that to which area of the space the orbit is visiting, how often it is visiting, that is, what is the frequency of visiting to a specific region of the space, where it is actually spending most of its time, and questions like that one can ask from itself about the orbit. To see that these questions are not always very easy, like to figure out the frequency, let's see a couple of examples. So I have the first example, which is very obvious, and from which one can see that the orbit is just nothing but a point. And the distribution and whatever thing the question that we ask are very easy to deal in this case. But that's not always the case. Let's make a little bit of Let's increase the difficulty a little bit and introduce another example, which is still an affine case. You see the constant derivative is still constant. I have a map f from the interval 0, 1 to 0, 1 defined by 2x mod 1, and I would like to recall you what does I mean by the mod 1. So mod 1 mean keeping the number to decimal. So you have 5.3 and 5.3 of mod 1 is forgetting about the integer part, and you just have 0, you just got 0.3. So 5.3 mod 1 is just 0.3. The graph of this function f of x is equal to 2x mod 1 is actually that I have represented it in the figure. I have I have sketched it in the figure graph of f, and I have choose randomly a point x naught and have sketched its orbit, that how its orbit is behaving. So I start from a point x naught in the first half of the interval, and its image x1 still lies in the first half of the interval, and its next image went to the second half of the interval. It's the image of x2, x3 still remain in the second half of the interval. X4 still remain in the second half of the interval. X5 come back to the first half of the interval, and so on. But there is no such a explanation through which so far that the topological explanation through which I can see that what is actually the orbit doing, how much time it is spending at a particular area, what is the frequency, in other words, what is the frequency of proceeding to a specific area, what are the statistical properties of the orbit. These questions are now not easy to understand, although it's still a simple dynamical system, just in a fine map. So from this we can easily see that when we have a little bit of different dynamical system, the description of the orbit, the distribution, the statistical distribution of the orbit, or other properties of the orbit can get much more worse. And in fact, toward the very end, just for the sake of to show you the power of the ergodic theory, toward the very end of the course, we will actually figure out that there exists a tool which I would later call it physical measure for this dynamical system, and which describe the statistical distribution of almost every point. In fact, we can also prove, we will try, hopefully we will get much time to prove this result at the very end, that Lebesgue, almost every point in the interval 0, 1 is actually dense in the interval 0. By that I mean that there exists a major zero set such that out of that major zero set, the orbit of each and every point can reach to each and every other point in that interval. That is, there exists a subsequence in the orbit of the initial point x naught, such that it converges to another point in that interval. And that's what we will actually, these two concepts that I mentioned, that there exists a tool which describes the orbit of almost every point. And this result, we will try to prove it towards the very end of the course. So we saw that in fact describing the orbit is not very easy, and we need much more tool to describe it. And the tool that we need so far is physical measure. So physical measure is actually, for the moment, you can think of physical measure is like some instrument you got, and then you have hold upon a huge number of the orbit, and you can describe a huge number of orbit just through that too. But I must warn you that getting a physical measure or achieving a physical measure for a dynamical system, even under very specific condition, like you have an example, just not in a generality, is always very difficult to get a physical measure for a dynamical system. And in fact, getting a physical measure, as I mentioned, it's extremely difficult. But in our course, we will get the physical measure for a specific class of dynamical system while imposing much more condition, and for those kind of dynamical system, you will achieve the physical measure. And in the way in which we are going to achieve this physical measure for those system is actually, we will work in a way like somebody who is trying to reach to a higher position while using stairs. So we will have stairs. So the first stairs, then the second stair, the third step, and then the first step, second step, third step, and through the stairs we will reach to the physical measure. So in this case, in the mathematical terminologies, our steps will be We will have invariant measure, we will have ergodic measure, and we will have some other condition of the space, and then through with the help of these, we will reach to the higher stage, which is the physical measure. So these were a bit of motivation. I hope you guys have got a little bit of interest in this, and let's go to introduce a couple of important things that we need throughout the course. So the very first thing that I would like to introduce is the space of probability measure. So the space of probability measure, I mean a measure such that the measure of the whole space is space lies between the interval 0 and 1. And due to which you can think of the measure mu in this case, which is a probability measure, is just like a probability function as we used to study it in the course of statistics. In fact, it's very easy to see that this space of probability measure, or a probability measure, is actually a convex set. And this, because of this, if we have even 2 points in the space X, we get an uncountable collection of the space of probability measure. An uncountable collection in the space of probability measure. So to see this, I would like to recall you the Dirac delta at some particular point X. So let me tell you how was the Dirac delta defined. For the moment, you think of you have the space R, real number, you have the sigma algebra beta, and you have the Dirac delta at the point 0 measure. So for any measurable set in the sigma algebra, the Dirac delta at the point 0, you can of course define it at point 1/2 or whatever point. At the Dirac delta evaluated, Dirac delta at the point 0 evaluated at the set A is either 0 or 1. 0 in the case when the point 0 is not in the set A, and 1 in the case when the point 0 is in the set A. So this was the definition of the Dirac delta. Now, as I mentioned, that when you have even just 2 points in the space X, you get an uncountable collection of probability measure. And how you get this combination, how you get this uncountable collection? You choose these 2 points, you choose the Dirac delta associated to these 2 points, because the Dirac delta at any point is actually a probability measure, as we saw in the other slides. And then you, since it's a convex set, so all the combination of these linear combination party in the interval 0, 1 are again in the space a probability measure. And since t is in the interval 0, 1, you get an uncountable family of probability measure, just even you have 2 points in the space X, which tell us that actually dealing with measure is not easy to resolve the problem, because you have uncountable family of measure, and then you have to choose a measure which work for your system. But we will impose further more condition which will make it easy for us, that not every measure we are going to choose from the space of probability measure, but we will choose some specific measure from the space of probability measure which will describe the dynamics of that system. Another important thing, the weak star convergence. So those of you who know the weak star and weak star topology, so for them it's just an introduction, just recalling. And those who don't know the weak star topologies in the dual of a space, I would recommend to them that you just need to remember the point 1, the equation 1. So there is this Markov theorem which says that for a space, the space or the space of measure for a space X is the dual of the space of continuous function. And the important thing in this slide is to understand that what does we mean by the convergence of the sequence of probability measure to some other measure. So you have a sequence mu n probability measure or whatever measure, but in dynamical system we mostly deal with the probability measure. So you have a sequence of probability measure. What does it mean that this sequence mu n converges to another mu? So we say that a sequence mu n converges to mu if and only if the integral for any continuous function p associated to mu n converges to the integral associated to mu, and that's for all continuous function over the space X. So we just need to remember this definition, that what does we mean by the convergence, the weak star convergence, or the convergence in the space of probability merge. There is another important theorem which says that if X is compact, then the space of probability measure is also compact. And both of these results you can found in the book by Brazes, functional analysis in several spaces. I will attach the link as well. But yeah, you can find this book online. Another concept that we need is Dirac averages. And Dirac averages, so let's recall the orbit again, the setup point which we are getting from the forward images, and the Dirac averages is actually for finite number of element of the orbit for the first, for example, for the first n element of the orbit. Dirac averages is the average of the Dirac measure associated to each element in the first n element of the orbit. So in fact, you assign to each and every point up to the to each and every element of the orbit until the nth element, and then you form the average. In order to understand this equation too, I will give you two different approaches. The first one, which is the short-term understanding of this thing, and the second one, which is the long-term understanding of this equation too. So let's figure out what does actually the Dirac averages is telling us, and what does actually it mean in the short-term sense. You see, the Dirac averages is a linear combination of the Dirac measures, and as we saw that being a convex, the space of probability measure being a convex space, still the Dirac average is a measure. So if we are evaluating the Dirac averages at a particular set A, measurable set A, then it will actually giving us the number of time, the average of the number of time the orbit is spending in this particular set. How? So you evaluate for a particular set A, the right side of the equation, the Dirac delta at the point xi will give you either 1 or either 0. 1 in the case when the point xi is in the set A, and 0 in the case when the point xi is not in the set A. So actually, I'm counting the number of time the orbit until the nth iterate, until the first n among the first n element of the orbit. I'm counting that how many times is the orbit falling in the set A. When it is falling in a set A, I'm counting 1, and if when it is not falling, I'm ignoring it. So in a sense, the short-term meaning of this is actually you are trying to find out the frequency out of the first n element of the orbit, the frequency of falling the orbit in the set A out of the first n element of the orbit. And that's actually now you can get a little bit of relation to the very first questions that we asked, that we actually asked, and was that what is the frequency? What is the frequency of the orbit visiting to a specific area of the space? So from the short term, at least so far, from the short term meaning of the Dirac averages, you can see that we can resolve the problem and we can understand the problem by only dealing with the Dirac averages. For the point x naught, when x naught is a fixed point, it's very easy to see that the Dirac averages is either giving you 0 or either 1. Again, in the same situation, when the point x naught is in the set A, and when it is 1, and when it is not in the set A, it's giving us 0. Now, let's go to the long-term meaning of the Dirac averages. As I mentioned earlier, the Dirac averages at a fixed point. Well, so you see the summation. The summation is just nothing, but it's the Dirac, since the orbit of the point x naught is just that element again and again. So the Dirac averages is just converging to the point, the Dirac delta at the point at the fixed point. In fact, not converging. In fact, equal to the Dirac delta at that point. But to make it a bit more clear in something which you can understand, let's see another example. I have the map F. dynamical system from the interval 0, 1 to 0, 1, and the map is defined as 10x mod 1. So just you can think of the map 10x mod 1 is shifting the decimal toward the right by 1 decimal. So when you apply the map f on the point some point, so let's say for example the point x naught as we have in the slide, so it will shift the decimal toward the right and will ignore the integer part. Will shift the decimal toward the right and will ignore the integer part. So it's actually the translation of the decimal point and ignoring the integer part. So when you have the point x naught, you are getting that in the weak star sense. In the weak star sense, you can get that the Dirac averages for this point x naught is actually converging to 1 over 3 of the sum of the Dirac delta at the point x naught, x1, and x2. Well, x1 is the point 0.12012, x2 is the point 0.2012012, and so on. And what does actually the orbit is doing? Let's see the distribution of the orbit. So it's actually a periodic point. You have 3 points x naught, x1, and x2. And what is the orbit doing? From x naught to x1, from x1 to x2, and from x2 to x naught again, and traveling in the same way and spending equal amount of time throughout its journey at each and every of these points. And this is what actually the limit of the Dirac average is also telling us, that throughout out of the whole journey, 1/3 proportion of the time is actually the orbit is spending 1/3 proportion of the time at the point x naught, 1/3 at the point x1, 1/3 at x2. In fact, this is telling us that the whole weight is distributed among the point x naught, x1, and x2. So 1/3 of that lies at the point x naught, 1/3 lies at the point x1, and 1/3 lies at the point x2. So somehow they are now kind of related, that what is the limit of the Dirac average is telling us is actually the behavior of the orbit as well. So we are making some ways to transform the problem of understanding the behavior of the orbit to understand the limit of the Dirac average so far. In order to make it much more clear, let's deal with another point. So I have the same dynamical system, which is the 10x mod 1. You can see the graph. And I choose the point x naught, which is 0.x naught, and then all the past, all the one-digit numbers. Then I have 100, 0, and then all the two-digit combination, like 0, 1, 0, 2, 0, 3, up to 999, up to 99. And then I have much more zeros, 100,000 zeros, and then again the three-digit combination, and so on. So one can see easily, as I mentioned, that it's just a translation of the decimal and ignoring the integer part. The map is acting like that. So one can see that the orbit is traveling actually to many other regions, but most of the time it is spending around in the neighborhood of 0. And this actually what's the limit of the Dirac average is telling us, that you have put the whole weight in this situation, you have put the whole weight on 0. So the orbit is traveling to many other places, but most of the time it is spending in the neighborhood of 0. In another word, statistical distribution is there, that up to a negligible amount of time, the rest of the time is actually in the neighborhood of 0. So these were the long-term behavior of the orbit. Let's go now to introduce another concept, which is Bayesian. So the Bayesian of attraction of a probability measure mu. So the Bayesian of attraction is actually a subset of the space X. One should notice that actually it's a subset of the space X. But the way how you will declare a point to be in the Bayesian is actually dependent on the space of probability measure. So the Bayesian of attraction associated to a measure mu, probability measure mu, is the set of all those points in the space X such that the Dirac averages associated to that point is converging to that measure mu. And of course, the convergence is always the convergence of the measure is in the weak star sense. So let's see an example in order to understand this. I have a map, a dynamical system f from the interval 0, 1 to 0, 1, which is defined f of x equal to x square. And one can see that the Dirac averages, the sequence of the Dirac averages is actually converging to the Dirac delta at the origin. And F1C, the distribution of the orbit for each and every point except the point 1, then it's also telling us the same, that for the each and every point other than the point 1, the orbit of that point is converging to 0, except for the point 1. So this is also ensuring the previous concepts as well. But now we are looking for the point which lies in the basin. So we saw that the Dirac averages for each and every, this is very easy to understand. You just need to do a little bit of computation. So the Dirac averages at a point x per every point in x naught is actually converging to the Dirac delta at the point 0. In other words, for each and every point in the interval 0, 1, it shouldn't be the closed interval from the right side. It should be 0 close and 1 open. For each and every point, like another one, for almost every point in the interval 0, 1, the Dirac averages converges to Dirac delta at the point 0. So the basin of attraction, attraction of the Dirac delta at the point 0 is actually the whole space except the point 1. Now, our definition of physical measure, the tool that will describe the statistical distribution. For any probability, for a probability measure mu to be called it as a physical measure, the condition is that the basin of attraction need to have positive Lebesgue measure. One should notice that now we are dealing with two measures at the same time. The measure under consideration, which is mu, and another measure, which is the reference measure, the Lebesgue measure. So the basin of attraction can have full measure with respect to the measure mu, but it might have zero measure with respect to the Lebesgue measure. We will not deal with the measure of the basin of attraction with respect to the measure itself, but we'll deal with the measure of the basin of we'll deal with the Lebesgue measure of the basin of attraction. Being the Lebesgue measure being positive, will declare it that this measure is a physical measure. To see this, one can see that when you have a contraction and a unique fixed point, then almost every point is converging to that fixed point, is like we see in this example. And for this kind of contraction, we're having a unique fixed point. One can easily see, as we saw in this example, that the basin will have positive Lebesgue measure. As in this example, 0 was a attracting fixed point, and the Dirac averages for each and every point except the point 1 was converging to the Dirac delta at the point 0. So this example is also the same when you have a fixed point for a contraction, a unique fixed point for a contraction. But it's not always true that a system must have physical measure. For example, a very simple system, which is the identity map on the interval 0, 1 or over the circle. You can think of it as a circle. By circle, I mean you just identify the in point of the interval 0, 1. This system doesn't have physical measure. Very easy to figure out, because you can see the orbit is just that point. But still, you can also figure out the point in this example. I would like to leave this. I would like you to notice this, that for this example, the basin of attraction associated to any other measure, like say the Dirac delta at the point 1 over 2. For this example, the basin will have full measure with respect to itself, but will have zero measure with respect to the Lebesgue measure. So this should be an important point which we need to focus on as well. Now, as we were claiming that the physical measure will be a measure which will describe the statistical distribution of much more points. In fact, now you can see that we will have quite huge class and huge number of points, which is like having positive Lebesgue measure, such that the distribution of the orbit of those points will be described by that measure mu. And that you can see from this example as well. Just for the sake of understanding, you can see that the Dirac delta at the point 0 is a physical measure. The Basin of attraction is almost everything except the point 1, and you see the Dirac delta at the point 0 is describing the statistical distribution of each and every point, except of course point 1 is the fixed point, so we shouldn't deal with it. But it's the Dirac delta at the point 0 is telling us that it's a unique one in this case. So it's telling us that actually you have put all the weight at the point 0, and almost all the points, the orbit of almost all the point spend most of its time near 0 or in the neighborhood of 0. So this will be a situation for each and every physical measure that the point which is lying in the basin of attraction of the physical measure, then the orbit of that point will be described by that corresponding physical measure. But we will deal with these kind of things in the future talks as well. Now, in order to motivate it a little bit more, like to give you some kind of magical statement, I would say so far, because it's a conjecture. This conjecture, the Palis conjecture, says that most systems have finite number of physical measures, such that the union of their basin have full Lebesgue measure. So, for the moment, there is a hope to see that most system. Well, that I wouldn't go to explain the most system because I need further more tool. But for the moment, you can think of it as the most is the English word most. So most systems have finite number of physical measure such that the union of their basin have full Lebesgue measure. So from the very beginning, what we start that to describe the orbit, we need a tool. This tool is physical measure. Now this conjecture is telling us that most systems have finite number of physical measure. So you just figure out all those finite number of things. You just deal with those finite number of things, and you get explanation to uncountable number of orbits, uncountable number of problems, and you just need to deal with finite number of things. So this conjecture is in fact another motivation which is telling us the importance of the physical measure. And when you have a dynamical system, then this is expected, I would say, that it will have finite number of physical measure. And as far as you figure out all this physical measure, then you have everything in your hand. You are able to describe statistical distribution and all other more other important property that we will see in the future of the orbit of almost every point, because this is also telling us that the union of their basin have full Lebesgue measure. So you combine all the basin, it's covering the whole space. So when it's covering the whole space, you have for every point you have a physical measure, and you can describe the behavior of the orbit and properties of the orbit with the help of that physical measure. Okay, let's go to introduce another concept. I will now go toward the proof of the theorem, and as I mentioned, that this will be the first step toward the physical measure, which is the invariant measure. So I introduce a concept which is called push forward, and the push forward of any measurable map H from a space X to Y metric space. And the push forward is represented by H star. It's a map from the space of probability measure associated to the space X to the space of probability measure associated to the space Y. So for any measure mu in the space of probability measure associated to the space X, it is giving me H star mu in the space of probability measure associated to the space Y, and it is defined as in the following way: that H star mu of A, or any A in the space for any measurable set in Y, is defined as like this. So you basically pull it back through H. H is a map from X to Y. So you choose a set A, measurable set in Y. You pull it back to X. Now, since the measure mu was a probability measure over the space X, now you can figure out its image. So with the help of this pulling back and taking the image, you have like a kind of, you are pushing your measure a measure to the another space. Together with this, I will introduce another terminology, which is paradynamical system XF. I introduce MF of X is the space of all measure, probability measure, which are the PEX point of the map F, the PEX point of the push forward of the map F. So these measure are also called invariant measure. We will throughout the course we will call them invariant measure. So for the dynamical system, the the fixed point of the push forward of that map are actually invariant measure. Now let's go to the very final thing in the today's session. Theorem. Theorem say that for space X and continuous map F, every limit measure up to. Remember, 2 was the Dirac averages. So every limit measure up to is a fixed point of the push forward of that continuous function. So let's prove this theorem in a nutshell. It's quite easy to deal with it. So you start from 2. 2 is actually the Dirac averages for any point x naught. The Dirac averages as we defined earlier. And you can see that I can write the Dirac averages associated to the point xi in the following sense. Just a little bit of computation, you will be able to figure out that actually you can write it like this. Now one can think, one can see that the push forward associated to a continuous function, remember, associated to a continuous function is actually continuous. I can, it's very good exercise, but let me show you how to prove this. Yeah, so I have, you can see f star is continuous. I have a sequence which converges to a sequence of measure, probability measure, which converges to a measure mu. And in order to show that f star is continuous, I need to show that the image of this sequence also converges to the image of the limit. So the convergence is of course in the weak star sense, and the weak star sense I need to prove that for all continuous function p, the integral associated to f star mu n is converging to the integral associated to f star mu. But it's very easy to see that the left side of this convergence is actually this one. After a little bit of observation and a little bit of computation, you can figure out this very easily. And since f was a continuous function, this was one of the assumptions that f is a continuous function, p is a continuous function, their composition is a continuous function, and I know that the sequence mu n is converging to mu in the weak star sense. So from this, I can say that this integral is converging to this integral because p composed with f is still a continuous function. And then using the same technique, I can write it as like this. And in other words, I prove that this integral converges to this integral, which ensure that f star mu n is converging to f star mu. So we prove that associated to a continuous function, the push forward is always continuous. And then another observation is that you can write that the push forward of the Dirac averages, you can write it in the following way. The Dirac average is associated to the point x naught in this term. So what I have done, you see, from the summation in the first row, I have, since I took the image, so the summation is now starting from the point 1 and going to n. So I need to insert the initial point and need to remove the final summand. The initial and the final summand, I need to insert the initial summand and need to remove the final summand. That's what I have done. So I inserted and remove the initial and remove the final summand. I got this, and this is the balancing terms. You can see that this term is going to 0 under the weak star convergence, but you need to deal with this portion of the equation. So since f is continuous, when you have a sequence mu n, as I have mentioned, that by every limit measure of the Dirac average. So I'm just taking it mu n, but you can think of it as a subsequence as well. A subsequence of that sequence, the Dirac averages, if it is converging to some other measure, it will work in the same way. For the moment, let me just take it as the whole sequence. So if the whole sequence mu n associated to the point x naught, the Dirac averages converges to mu. Then by the continuity of the push forward, the push forward of this push forward also converges to the push forward of the limit. So from this side, from the left side, we will get after the conversion, we will get the push forward of the limit, which is mu. So f star of mu, and from the right side, sequence mu n associated to x naught, the Dirac average is associated to the x naught is converging to mu. So from the right side, we will get when n goes to infinity, we will get mu. So combining both together, we will get that actually the measure mu, which was a limit point of the Dirac averages, is a fixed point of the map F. Shortly, for a continuous map, the limit, each and every limit of the Dirac averages is an invariant measure. Yeah, so that's all for today. I have some links and some references that you can find online, the foundation of ergodic theory, from which we will mostly study the course. Another beautiful course by Stefano Losato, an introduction to smooth ergodic theory. Of course, you can also find them online, and then a link to the Palis Conjecture, the book by Hemprezes, that you can also find online. So thank you so much. It was pleasure to deliver this lecture, and see you next time.